We're now going to start a new topic in 0007, which is matrices and vectors. To begin, here is a load of definitions. An m by n matrix is a rectangular grid of numbers with m rows and n columns. There are some examples at the bottom of the screen here. Here we have a 2 by 2 matrix, a matrix with 2 rows and 2 columns. Next we have a 3 by 1 matrix, 3 rows and 1 columns, and finally at the end here we have a 2 by 3 matrix, 2 rows and 3 columns. A square matrix is one which is n by n for some n, so this matrix here is square but the other two are not square. A height m column vector is an m by 1 matrix, so in the middle here we have a height 3 column vector, and a width n row vector is a 1 by n matrix for some n. So as an example, if we had 1, 2, 3 like this, that would be a 1 by 3 row vector, a width 3 row vector. Finally, some notation for sets of matrices and vectors. R to the n means the set of all height n column vectors with real number entries. And m subscript m times n of R is the set of all m by n matrices with real number entries. We also use a similar notation with a different set in place of R. So for example, if we wrote c to the n, that would mean the set of all height n column vectors whose entries were complex numbers. And if we wrote m 2 by 2 of c, again that would mean the set of all 2 by 2 matrices whose entries were complex numbers. We need some vocabulary for referring to particular entries of matrices. The ij entry of a matrix is the number in row I and column j. It's important to get those the right way round because they're perhaps slightly confusing. If you're used to the coordinates on a map, then often the first coordinate refers to how far across you go and the second coordinate refers to how far up you go. But here, the first coordinate, the I, tells you which row you're in, which is how far down you go in the matrix. So let's look at some examples. Here we go. What's this? Pause the video, tell me which coordinate it is. This is the 2, 2 entry, so no possible confusion there. But what about this one? So that is in row 2 and column 1, so that is the 2, 1 entry. And similarly, this thing here would be the 1, 2 entry because it's in row 1 and column 2. So row 1, row 2, column 1, column 2, column 3. There is another very common piece of notation that we use when we talk about matrices, which is that when we write that the matrix A is equal to bracket A subscript ij, what that means is we're going to use little a subscript ij to refer to the ij entry of A. This is very handy when we're talking about an arbitrary matrix and we want to discuss its entries. So if capital A was 2 by 2, then it would look like this. So the 1, 1 entry here is A 1, 1, the 1, 2 entry is A subscript 1, 2. This is the A 2, 1 entry and this is the A 2, 2 entry. One thing that we do with matrices of the same size is to add them. And the definition of the sum of two matrices is just the matrix that you get by adding the corresponding entries. Another way to phrase this is by talking about the ij entry for an arbitrary I and j. So if A is a matrix whose ij entry is little aij, and B is a matrix whose ij entry is little bij, and those matrices have the same size, then A plus B is the matrix whose ij entry is the sum of the ij entry of A and the ij entry of B. So for example, if you have 1, 2, 3, 4, the 2 by 2 matrix 1, 2, 3, 4, and you add it to the 2 by 2 matrix 5, 6, 7, 8, then what their definition says is that you add the corresponding entries of those matrices. So the 1, 1 entry of their sum will be the sum of the 1, 1 entries of those two matrices, which is 1 plus 5. And the 1, 2 entry of the sum will be the sum of the 1, 2 entries of the two matrices, which is 2 plus 6, and so on. We also do what's called scalar multiplication of matrices. If you have a matrix A whose ij entry is little a subscript ij, and if you have a number lambda, then the matrix lambda A is the matrix whose ij entry is lambda times the ij entry of A. So to form a scalar multiple of a matrix, you just multiply each entry of that matrix by whatever scalar you're multiplying by. At the bottom here is an example. We're multiplying the matrix 1, 2, 3, 4 by the scalar 1, 2, and to work that out you just multiply each entry of the matrix by that scalar minus 2. So the result will be minus 2 times 1, minus 2 times 2, and then on the next row minus 2 times 3 and minus 2 times 4. So those two operations are called matrix addition and matrix scalar multiplication. Finally, let's look at a few of the rules which control how scalar multiplication and addition interact with one another. So there are some very simple rules which I don't intend to prove for scalar multiplication and addition. If you'd like to see proofs of those, you can find them in the online notes. So first of all, there is a distributive property. If you scalar multiply A plus B, the number A plus the number B into the matrix A, then the result is the same as doing the scalar multiple A times A plus the scalar multiple B times A. Okay, next up, if you do a scalar multiplication into a vector addition, so a scalar little a multiplied into a matrix sum capital A plus capital B, then the result is the same as doing little a times capital A plus little a times capital B. And finally, there is what's called a associativity law. So if you do a scalar A times a scalar B times a matrix A, that's the same as doing the scalar multiplication, so multiplying the two scalars rather, A times B, and then multiplying the whole lot into A. And if you just think about the individual entries of the matrix, then all of these three rules follow from standard properties of multiplication of real numbers or complex numbers. We have another definition here, which is of the m by n zero matrix, which is just what the definition suggests. The m by n zero matrix is the m by n matrix, all of whose entries are 0, and we write it as 0 subscript m times n. And of course the special property of zero matrices is that when you add them to another matrix, you just get the same matrix again. So adding something to the zero matrix doesn't change it. Okay, final definition then is the transpose of a matrix. The transpose of an m by n matrix A, whose ij entry is little a subscript ij, which we write as A with a superscript capital T, is the n by m matrix, whose ij entry is the ji entry of A. Another way to phrase that definition is to say that the rows of A transpose are the columns of A, or alternatively, that the columns of A transpose are the rows of A. So let's see an example of this. Here is my matrix A. Okay, what's the transpose? What is A transpose? Pause the video and work it out. Okay, I'm sure you did that. A is 2 by 3, 2 rows and 3 columns, so a transpose should be 3 by 2. So it should look like this. Now the 1, 1 entry of A transpose is the 1, 1 entry of A, which is 1. The 1, 2 entry of A transpose is the 2, 1 entry of A, so that is 4. The 2, 1 entry of A transpose will be the 1, 2 entry of A, which is 2. The 2, 2 entry of A transpose is the 2, 2 entry of A, which is 5. The 3, 1 entry of A transpose will be the 1, 3 entry of A, which is 3. And finally, the 3, 2 entry of A transpose will be the 2, 3 entry of A, which is 6. So you can see here that what I said about rows and columns worked out. Here is the first row of A transpose, the first column of A transpose being the same as the first row of A. And alternatively, if you want to look at rows, then if we look at the second row of A transpose, that will be the same as the second column of A.